Now we get to the important concept of thrashing. So thrashing now is the issue, is the challenge in virtual memory allocation. And what thrashing means simply is that a process or processes are not getting enough frames, so they will be running into too many page faults. And if a process runs into too many page faults, it will be spending most of its time waiting for the system to service that page fault. Basically, it will be spending most of its time in the waiting queue for the device, for the disk, or with waiting for the disk to complete the transfer of data from disk to memory or from memory to disk. And the running time of the process will be dominated by page fault handling. So that's thrashing. So the process will not be spending much time doing actual execution on the CPU. It will be spending most of its time waiting for the system to handle a page fault. And remember that handling a page fault is very costly. It's in the millisecond range, and the millisecond range means millions of cycles. So it will be spending millions of cycles waiting for the disk and only a few cycles running on the CPU. Now, in order to explain thrashing, I would like to give this example, very simple example of a process accessing an array in a loop. So suppose that you have a 4-page array. You have an array that consists of 4 pages. Page 3, page 4. An array that consists of 4 pages. So maybe the array is 4K and each page is 1K. And you are accessing this array in a loop in a sequential manner. So you are accessing, so this is array called A of I plus equals 3. Now this array consists of 4 pages, but what if we have only 3 frames? What if this process is currently allocated only 3 frames? Now, how many page faults will happen? So let's see how many page faults. So first off, when the program executes the first loop, so let's assume that this is executed 1,000 times. I equals 0, I less than 1,000, I plus plus. So in the first iteration, these pages are not in physical memory yet. So we'll have a page fault, and we'll look for a frame for this. So this will get frame number 1. Then when we access page 2, it's not in physical memory yet, so we will give it frame 2. Page 3 will get frame 3. Now page 4, what will happen when the program accesses page 4?
Replace a frame.
Yeah, we need to replace because we have used all 3. So we need a replacement. Now this will depend on the page replacement policy. Assuming that we are doing LRU. With LRU, which page will get replaced? Page 1. So with LRU, we'll replace page 1. So now this will no longer be in frame 1. This will be on this. It will no longer be in physical memory. And frame 1 will be given to page 4. But now this is in a loop. So in the second iteration of the loop, the program will access page 1. When it accesses page 1 is not in physical memory. So this is the page 4. And we will need to find a frame for it. Now, which frame will it get if we are doing least recently used?
2.
Frame 2. So now this will get frame 2. And this will lose its frame. But next we will access page 2. And Page 2 will get a frame. Which frame will it get? Yeah, it will get frame 3. And then when we get to page 3, it will no longer have page 3, or frame 3. So it will get the least recently used, which is frame 1. Now, when we are here again, will there be a page fault? Yeah, because we just gave frame 1 to this. So again, this will not have its frame 1. So now, what percentage of page accesses in this loop will result in page faults? What percentage of page accesses in this loop will result in a page fault? Yeah, it's 100%. All of them. All of them are going to, assuming that it's least recently used, every page access will result in a page fault. Now, if we just increase the number of frames from 3 to 4, if we increase the number of frames from 3 to 4, how many page faults will happen, will take place in this loop? Only 4. Only in iteration 1. If you increase the number of frames from 3 to 4, only in iteration 1 you'll have 4 page faults. Then you will load them all in memory, and they will all be in memory, and you'll keep referencing them 999 times. So only in iteration 1 there is a page fault. In iterations 2 through 1,000, there will be no page fault. So this shows you how much of a difference the number of frames can make. So, and it also shows you here the difference between least recently used and optimal. Now, let's go back to this. When we get our first page replacement here, what would the optimal do? So this doesn't have a frame. So when we do optimal, optimal is not going to replace frame 1, because frame 1 will be used in the near future. It will be used next in the future. So optimal, which is a hypothetical algorithm that is impossible to implement, it's not going to replace page 1, it's going to replace page 3. Right? So it will minimize the number of page faults. But it's, again, optimal is impossible to implement. So you see now how much of a difference the number of frames makes. Now, the other important concepts here are the concept of locality. So the concept of locality here, when this program is executing this loop, it's in a locality only accessing these 4 pages. The program may have 1,000 pages or thousands of pages, but when it's executing this loop, it's only accessing a subset of these pages, which is these 4 pages only. So this constitutes the locality of the program, or the working set that this program had. So the working set for this program, when it's executing this loop, consists of only 4 pages. And in order for this program to run with good performance, I only need 4 frames. So the number of physical frames that I need for a program should be large enough to accommodate the current working set. Right? It doesn't have to be large enough to accommodate all the pages that constitute the program's logical address space. The logical address space of this program can have thousands of frames in it. But with the current locality, my working set is only 4 pages. Okay?